Interacting with your phone's virtual keyboard leaves behind specific typing signatures. Next word prediction systems rely on this data to map your unique habits. Training these intelligent models requires an immense volume of examples, but the raw inputs, your keystrokes, voice commands, and personal photos, are intensely private. The traditional distributed machine learning pipeline solves the data volume problem by uploading all of that raw user data to a centralized server, pooling it together for processing. Aggregating this much sensitive information creates a massive risk surface. A centralized repository becomes a high-value target, vulnerable to breaches by malicious actors. Modern data protection acts have responded to these risks. The legal liabilities surrounding the storage and processing of user data make centralized data lakes increasingly difficult for tech companies to maintain. Moving raw personal information from millions of devices into a single repository degrades user trust and creates significant security liabilities. Even if privacy concerns were entirely resolved, centralized machine learning fails on mobile devices due to physical hardware constraints. Unlike the controlled environment of a data center, the mobile edge relies on unreliable wireless connections with limited bandwidth and high latency. In these environments, the communication cost of uploading heavy raw datasets often exceeds the computational cost of simply processing the math locally. This bottleneck forces a structural pivot, an architecture known as federated learning. Federated learning reverses the traditional pipeline. Instead of moving the data up to the math, it moves the computational math down to the data. Training datasets remain permanently locked on the local device under the user's direct control. By processing information natively on the hardware where it is generated, this decentralized approach reduces bandwidth requirements and helps navigate the legal complexities of modern data protection acts. The mechanism driving this decentralized network is a specific algorithm known as federated averaging, or FedAvg. This map illustrates a standard FedAvg topology. A central server maintains connections with a vast pool of edge devices. Real-world mobile networks are asynchronous. Devices routinely drop offline due to low battery, meaning not all clients are available. To begin a training round, the server surveys the network and randomly selects a subset of active devices, 2 mobile phones and a tablet. It then broadcasts the current global model parameters, represented as WT, down to the selected clients. This packet contains neural network biases, the model architecture, and instructions like batch sizes. Notice the direction of the flow. No raw data or device-specific information is ever requested from the clients. This top-down synchronization ensures that every participating edge device begins its local training phase from the exact same mathematical baseline. Once the clients safely receive the baseline model from the central server, the actual learning begins in complete isolation. Looking closely at these nodes, local data volumes vary. Datasets are naturally skewed based on how often individuals interact with their devices. Each client uses stochastic gradient descent to calculate prediction errors against its private data. The iPad processes 200 distinct data points. M2, by contrast, only computes against 20 data points, resulting in a much shorter processing loop. This smaller dataset yields a potentially noisier update, but it still captures unique behavioral signals that larger datasets might lack. The output of this isolation phase is a newly optimized set of local model parameters for each specific device. The clients encrypt their updated parameters, WT+1, and transmit them back to the server, along with their respective dataset size counts. Throughout this cycle, raw user inputs and local gradients remain confined strictly to the edge hardware. The edge devices successfully improved the model locally, but their individual updates are entirely fragmented. They require synthesis to be useful globally. The central server now holds 3 distinct updates. It cannot simply average them equally, since the data volumes provided by each device are heavily skewed. The server first calculates the total dataset size for this training round by summing the reported counts. Next, it assigns a proportional weight to each client's parameters, based strictly on the volume of data they contributed. This yields the formal FedAvg equation, applying those percentages directly to the incoming uploaded weights. The math dictates that the iPad's parameters heavily influence the final result, naturally stabilizing the unbalanced data distribution without relying on manual tuning. This completes a single communication cycle, generating a globally accurate baseline model ready for distribution in the next round. The FedAvg aggregation engine extracts collective intelligence from disparate, isolated devices, seamlessly resolving the discrepancies in their local hardware. Even with raw data secure on the device, the system retains a vulnerability. Anonymous model weights can still be intercepted and analyzed. In a linkage attack, malicious actors reverse engineer aggregated updates. By cross-referencing multiple data points across different sources, they can potentially re-identify a specific individual's behavior. Closing this vulnerability requires an additional cryptographic shield, known as differential privacy. This chart demonstrates the mechanism. Differential privacy injects carefully calibrated random noise into the aggregated statistics, intentionally distorting the exact numbers to obscure any individual data point. Finding the precise calibration is a mathematical trade-off. Too little noise fails to protect anonymity, while too much noise destroys the model's predictive accuracy. The level of required interference is determined by the data's sensitivity, meaning the injected noise must scale proportionately to the highest possible variance introduced by any single participant. This variance mathematically blocks an attacker from isolating a specific update, making it impossible to verify if a particular user's data was even included in the training round. Pairing the decentralized computation of FedAvg with differential privacy allows engineers to train accurate, large-scale models while maintaining a mathematically provable level of user privacy.